All right. So it looks like we have a couple of questions in the Slack. And the first one is from Shuhao Luo. Shuhao, are you around? Perhaps while we try to find Shuhao, we have one from Yunfang Chen. Yunfang, you want to pose your question?
Yeah, hi, Sishuai, great work. And I want to know how does the Snowboard cluster the similar PMCs? Because how could you compare the syscall traces? Because even if you have different orders of the syscall traces, they may share the same or similar context for the kernel execution. So I noticed that there are some heuristics defined in the paper, but I'm still curious. How could you cluster or define the similar PMCs? Yeah, thanks.
Okay. Oh, that's a great question. I think let me put it in this way. I think ideally, let's say a kernel has X number of concurrency blocks. A perfect clustering strategy will give us X plus 1 clusters. And so each cluster of the first X clusters will trigger a unique concurrency block in the kernel. And the last one contains all the PMCs that don't trigger any concurrency blocks. That will be the ideal clustering strategy we want to use. And in the paper, we propose several heuristics based on the instruction, based on the memory address, based on different features of the PMC. And we hope that would be a proxy task to the ultimate goal. Does that answer your question?
Do you consider the sequence of the syscalls? Like if the sequence is different, then you could say that these PMCs are different. Do you consider the orders of the syscalls or the sequence of the syscalls?
Oh, we don't consider that. And I think the intuition behind is the order of system calls probably is less relevant to the actual PMC that could happen between these two sequential inputs. So for example, we have seen the same PMC could be triggered by different concurrent inputs. And based on different heuristics, based on different clustering strategies we propose, they might or might not be grouped into the same cluster.
I see. Okay, thanks.
Thank you.
Okay, we had a question from Chirag Shetty, who I saw moments ago, but
I am here. Yeah, hi. Thanks for the talk. So the question I had is I probably missed this, but the way you detect the PMCs, right? Won't the PMC differ based on, there are conditional statements and depending also on the interleavings, right? PMCs, and that's what makes it, the exponential, factorial number that you said. So how are you sure, like, how are you detecting it, and how are you sure that it covers all of these, memory accesses?
Oh, the kernel execution could be non-deterministic. That is true. And we saw that our solution is to always resume from the same fixed kernel state. So we could reproduce execution we observed during the sequential input analysis to the maximum extent.
Yeah, but also memory accesses may differ based on how the concurrency occurs. So when you are doing a single thread execution, depending on how you chose to order them, the PMCs may be different, right? So.
All right, the PMC could be different. And we have observed in the experiment that once a PMC can trigger one thread, maybe the reader thread, to execute some new code, which is not observed with the sequential analysis. And that could be possible. But our current exploring algorithm to explore interleavings is able to execute the new code. So the new code is still tested under once the PMC happens. And this is how we can find concurrency blocks. We want the reader thread to execute some new code, probably that have concurrency blocks.
Okay, so the entire tree is not kind of searched, but some parts are using a heuristic is smartly searched. Okay, yeah, thank you for that.
All right, we had a question also from Bogdan Stoika. Are you here?
Can you hear me?
All right. I think awesome. we can see you and almost hear you.
Oh, okay. Let me.
There you go.
Right.
There we go.
All right. Awesome. So I had two quick questions. One is more curiosity. The second is more for the, the algorithm. So my first question was, how do you deal with hardware inputs that might cause concurrency bugs? Do you handle that, or does Snowboard, do you plan to extend Snowboard to handle that, or does it handle it inherently?
Oh, just to clarify, the question is about the hardware input, right?
Right, yes.
And I think hardware input, that's a good question, by the way. And I think hardware can take two kinds of input. The first input is the system cost. We can execute some system cost to trigger the hardware to do something. And another input is that we can interact with the hardware directly. For example, send a packet to the network hardware. And currently, we only consider the system call input. And I think that should be generic. Our approach should be generic to hardware input if that input is the system call input.
I see. Awesome. Thanks. That clarifies. And then my second question was a bit about the algorithm. I saw that you use different clustering strategies. Sorry, I know you didn't talk this on the slides, but I read the paper. So, and except two clustering strategies, all the others are just finding one bug. And I was wondering if there is some sort of limitation that I couldn't figure out from the paper, and maybe you have some intuition about that.
Oh, so some of them, yes, we designed 7 clustering strategies in total. And in the evaluation, some of them did not find many bugs as the others. That is true. However, we didn't think that is a failure. We don't think the rest of clustering strategies are failures, because you were also able to find some kernel behaviors to concurrent behavior. For example, concurrent issues, for example, harmless data releases. So we think those clustering strategies are still useful at a certain context.
Oh, I see. Okay, that answers my questions. Awesome. So basically, you need to use all clustering strategies to find all bugs. That's the takeaway from Snowboard.
Yeah.
Yeah. Awesome. Thank you so much.
Okay, thanks for that question. I think we have time to squeeze in one more from Aditya Tiwari. Aditya, are you still with us?
Yeah, I'm still here. Can you see me? Yeah, so I guess my question is about like, how did you get code coverage when you picked your kernel initial states, and like, is there just one or are there several? And then are there some factors that you use to determine what a good potential PMC is?
Oh, that's a great technical question. I agree that the initial kernel state does have a great impact on the testing effectiveness. And one example I could give is, let's say if we did not mount a file system in that fixed kernel state, we will never be able to test that system. And in practice, we solve that by preparing complete initial kernel state by running some initialization tasks before taking a snapshot, before taking the fixed kernel state. And according to our evaluation, it works. Yeah.
All right. Well, let's thank our speaker. Well done. And let's move on to the third and final.
We see a question. So go ahead, Yinhong.
Hello, yeah, Sishuai. Thanks for the great talk. Yeah. So I wonder, when you cluster the different PMCs to reduce the number of the testing, how do you define the similarity among the different PMCs? Yeah. Could you elaborate a bit more? Yeah.
Oh, great question. Good question.
Yeah.
And let me put it in this way. I think if ideally, in the perfect world, if let's say if the kernel has X number of concurrency bugs, a perfect cluster strategy would give us X plus 1 clusters. So each cluster of the X clusters contain a unique concurrency bug. And the last one, the X plus 1 cluster, contains all the PMs that don't trigger a concurrency bug, right? That would be ideal. However, we currently, however, we haven't found a way to do that. It's very hard to achieve the ultimate objective. So right now we're proposing different heuristics to solve that question. We propose different heuristics based on different features of the PMC. For example, instructions, memory address of the 2 accesses involved in the PMC to cluster them. And the way I see them is there are proxy tasks to the ultimate objective.
I see.
So that's answer your question.
Okay, yeah, thank you.
Okay, there's no more question for now. Well, I have a question. How generous is your technique? How can you apply it to like other system other than the kernel?
Oh, I think our approach itself should be generic to all multi-threaded applications. And in fact, when I was thinking about that, I could imagine some challenges that we were faced with when testing a kernel probably will not exist when testing user mode applications. For example, controlling the interleavings or the instruction interleavings of user mode applications is much easier than controlling the kernel instructions. Right. That's what I saw.
Great. So there's another question. Howei?
Hi. Hi, great talk. So can I just ask,
Hi.
like, since your input is based on syscolor, what do you think about this eventually becoming part of the kernel continuous integration infrastructure, like syscolor itself?
Oh, I'm definitely happy to do that. And I think if syscolor developers at syscolor side is likely to accept our commits, and I would be very happy to merge that into the normal task that is running on Linux kernels. Right. That is what I thought.
Thank you.
So another question, Pao.
Hello, Sishuai. Thanks for the talk. I had a questions. So it obviously is clear that your results are dependent on the initial kernel state that you use before you do the execution and collect data. How do you determine what kernel state to use and how to find one that has an environment that can that may or may not affect the concurrent execution of the threads?
Great question. So let me just clarify that. I think the phased kernel state does have a great impact on the testing effectiveness. One example I could give is, let's say if we did not mount a file system in that phased kernel state, we will never be able to test that phase, right? Even with Snowboard. And in practice, we try to solve that question to have a more meaningful or complete initial kernel state by running some initialization tasks before taking the snapshot, before capturing the initial kernel state. And I think that is a common practice by most software testing work, or kernel testing frameworks.
Okay, thank you.
All right, so Howei, do you have another question? Okay, you're good. Well, if no more question, then we'll move on. Thank you for the talk.
You're welcome.
All right, so our next presenter is Ye Chen Bei, and